Meredith Townsend speaking to present thermomechanical models as a framework to study the evolution of magma chambers using constraints from petrology, geophysics, and geodesy. Before I get started, I want to acknowledge all the co-authors who have been part of this work, especially Chris Huber, who has initiated and spearheaded these efforts, as well as Kate Schultz, Catherine O'Hara, Olivier Bachmann, and Juliana Trock. One of the challenges of volcanology is that our main tools for understanding volcanoes come from diverse disciplines and datasets that span widely different timescales. On the one hand, we use geophysical methods to investigate the present-day state of a volcano, with measurements that span daily to decadal timescales. For example, we can use geodesy to detect surface deformation in active volcanic settings. Volcanoes commonly undergo episodes of uplift related to magma accumulation in shallow crustal reservoirs. Surface uplift usually precedes volcanic eruptions, though not always, although uplift often occurs without culminating in an eruption. Now, there's growing evidence that these episodes of magma recharge and surface uplift occur periodically over longer timescales to build up magmatic systems. For example, at Laguna de Maule in the southern Andes, there's a deformed paleo shoreline consistent with about 50 meters of uplift over the last 10,000 years. Aside from a few examples of this type of geomorphic data, most of our records of volcano deformation span at best a few decades. But we can also look to the rock record to decipher how the volcano has behaved in the past, over timescales of thousands to even millions of years. And one thing we see is that the size and frequency of eruptions can vary dramatically over time. At Laguna de Maule, for example, there have been a couple of anomalously large caldera-forming eruptions, but then in the last 23,000 years, eruptive activity has been concentrated into two phases, where the later phase has had a lower eruption frequency but greater eruptive volumes. Eruptions also sample the magma reservoir at different periods in time, and so we can use petrology or geochemistry to infer how magma storage conditions evolve over time, which might help us to understand where the system is today. Now alone, neither geodesy nor petrology gives us a full understanding of a system, but combined they might be able to provide a more complete picture about how volcanoes work. So today I want to show how numerical modeling of magmatic systems may serve as a promising tool to unite diverse data across different timescales. I'm going to start by reviewing a magma chamber model originally presented by de Gruyter and Huber in 2014 that has the potential to integrate both geophysical and petrologic data. Then I'll review some of the most significant insights we've gained using this model, and finally I'll present two new developments. These are the addition of carbon dioxide and the coupling of the magma chamber model to a model for surface deformation. In 2014, Wim de Gruyter and Chris Huber put together a simple but powerful box model for a magma chamber, with the goal of tracking the coupled thermal and mechanical evolution of a chamber subject to recharge and eruptions. Some of the questions that this model seeks to address include: what controls the frequency and size of volcanic eruptions? How and where in the crust can magma chambers actually grow? In a given model setup, the modeled magma chamber is at some depth in the crust, which determines the initial pressure and far-field temperature. The magma chamber is given some initial volume and water content. And then magma recharge occurs at some rate, m dot n, which delivers a fresh mass and energy to the chamber. Heat is conducted radially outward to the crust, and then cooling within the chamber leads to crystallization and volatile exsolution. The crust is treated as viscoelastic, with an effective viscosity that depends on the temperature profile. The governing conservation equations are solved numerically, and the model output is essentially a time series of chamber pressure, the volume fractions of crystals, melt, and gas, and the magma chamber mass and volume. So for example, here, for these initial chamber and recharge conditions, we see the pressure building up, and then when it reaches some critical overpressure, here set to 20 megapascals, the pressure drops again during an eruption. Also in this example, the crystal and gas volume fractions fluctuate but are overall increasing with time. And we end the simulation when the crystal volume fraction reaches 50%, after which the magma is less likely to move as a fluid. And then in this last time series, this is the change in chamber mass, which also builds up and then drops during an eruption. But in this particular case, the eruptions are smaller than the recharges, and so over time the chamber grows. Now, since 2014, there have been many more developments on this model, such as the transition between volatile undersaturated and volatile saturated states, volatile outgassing, and the coupling of the magma chamber model to a dike model. The first major insight from the model is that there are three regimes that govern eruptive behavior, and these regimes are broadly delineated by the timescales of the dominant processes. These include the timescale for magma injection, which is smaller for greater magma recharge rates and smaller chamber volumes. The timescale for magma cooling, which is also shorter for smaller chambers. And the timescale for viscous relaxation of the crust, which describes how fast pressure in the chamber is diffused by deformation of the crust. Now, a convenient way to visualize the model results within this framework is using the regime diagram on the right, where two of the timescales are compared on either axis. And for convenience, we break this diagram into three regions based on which timescale is the shortest, or which process is the fastest. So in the upper left, cooling is the shortest timescale or the fastest process. In the upper right, magma injection is the fastest process, and in the lower region, viscous relaxation is the fastest process. These two blue arrows represent how the timescales change when we increase the chamber volume or the magma recharge rate by one order of magnitude. So as the chamber volume increases, both cooling and injection become a bit slower compared to viscous relaxation. So a system will tend to go farther towards the viscous regime as it grows in size. Now, if magma supply rate increases, the system will tend to go towards the injection regime. If we look at the number of eruptions that occur before the magma chamber freezes, we see that most eruptions occur in the injection region. Only a few eruptions occur in the cooling region, and no eruptions occur in the viscous region because pressure can't build up to that critical amount. The second key insight is that magma chamber growth is also controlled by these timescales. Basically, to grow a magma chamber, you need both magma injection and you need the crust to be able to accommodate that new magma. So as a result, growth is enhanced in the lower right of this regime diagram, where both magma injection and viscous relaxation are fast. This is consistent with larger magma chambers, greater magma recharge rates, and lower viscosity crust. Farther up and towards the cooling regime, magma chambers can actually shrink over time, even when constantly recharged. Fast cooling leads to earlier volatile saturation, and the presence of a highly compressible volatile phase leads to eruptions that are greater than the recharges. This regime is consistent with smaller chambers, lower magma supply rates, and these chambers tend to shrink over time and freeze quickly. If we compare the results for eruptions and chamber growth, we find that the intersection of chambers that can both grow and erupt is decently narrow in the regime space, and it occurs where magma injection only barely outpaces viscous relaxation. If magma chambers are slightly farther into the viscous regime, they can grow easily, but they can't erupt. And if they're slightly towards the cooling regime, they can erupt, but they might shrink and won't be stable for long in the crust. So one implication of this is that the depth in the crust should have a major impact on whether or not chambers have that sweet spot to both grow and erupt, and for what magma chamber volumes and recharge rates this sweet spot occurs. So increasing the depth of magma chambers should push all systems down into the viscous regime. On the other hand, bringing systems to shallower depth would pull them upwards in regime space, closer to the cooling and shrinking regime. So we test this idea more formally in Huber et al. 2019, and we find that this sweet spot in the crust is enhanced at approximately 8 kilometers depth, or 2 kilobar. And this is consistent with petrologic and geophysical data that indicate that this depth of about 2 kilobar is generally where we tend to find subvolcanic magma reservoirs. So how can the model be used explicitly to integrate geophysical and petrologic data? Well, if we revisit the model inputs and outputs, we see that most of these parameters can be constrained or compared to one or more types of data. For example, melt inclusions can be used to constrain the PTX conditions in the magma chamber, and geophysical imaging may be able to provide some additional constraints on the depth and size of a magma reservoir, at least in its current state. One of the key findings from the modeling work is that the frequency and size of eruptions ought to scale with these parameters in consistent ways. For example, the eruption frequency should scale proportionally with the recharge rate and inversely with the chamber size and magma compressibility, whereas the volume of an eruption in a dense rock equivalent sense should scale proportionally with the chamber volume and the magma compressibility. What this means is that potentially trends in the frequency and size of eruptions may provide additional constraints on these parameters. So as a quick example, coming back to Laguna de Male, between the first and second phase of eruptive activity in the last 23,000 years, there was a drop in the average eruption frequency by a factor of about 6, and at the same time there was an increase in the eruptive volumes by an order of magnitude. Now, employing the scaling relationships suggests that the increase in eruption size and the drop in frequency could be partly due to an increase in the size of a magma reservoir. For Laguna de Male, an increase in chamber size over time seems reasonable, since we have that independent evidence from that uplifted shoreline indicating the addition of material throughout the Holocene. Now, the first of two recent model developments I want to highlight is the addition of carbon dioxide. This has been the primary work of Kate Schultz and Chris Huber for Kate's senior thesis at Brown University. So even though CO2 tends to be present in smaller amounts compared to water, its presence strongly decreases the solubility of water, and so it plays an important role in the onset of volatile exsolution and the rate of magma crystallization. On the right is an example of the new model output for a magma chamber near the border between the cooling and injection regimes. Now, for the case with only 100 ppm CO2 and 3 weight percent water, the magma never reaches volatile saturation. But we can see that when the CO2 increases to 500 ppm, the magma eventually does reach volatile saturation, at which point the exsolution of that highly compressible gas phase leads to a drop in the eruption frequency and a slightly faster rate of cooling. The second recent model development is coupling to surface deformation. So over the summer, I implemented the model of Bonafede and Ferrari for deformation in a viscoelastic half space due to pressure changes in a spherical source. Adding deformation lets us test what signature at the surface we might expect for different magma recharge scenarios, magma chamber conditions, and over different timescales. So for example, here are shown 3 different magma injection scenarios ranging from very impulse-like to more gradual, and all of these are occurring on fairly short timescales, less than 50 years. And we see that over these shorter timescales, in which the chamber behavior is elastic, surface uplift is enhanced for the shallower chambers and the drier chambers. However, in this model, we're actually calculating pressure in the chamber, and what we find is that for a given recharge rate, pressurization is faster in chambers that are smaller, drier, and shallower in the crust, which means that by the time pressure builds for an eruption, less deformation has actually accumulated in chambers that are smaller, drier, and shallower. And so as a result, over multiple eruption cycles, the trends in deformation rates are actually reverse what they are over a single injection episode. That is, uplift rates are greater for larger and deeper chambers. So in summary, we have lots of different types of data to investigate volcanic systems, recorded on dramatically different timescales. And numerical modeling of magma chamber evolution, such as the work shown here, may be able to provide a unifying framework with which to integrate these data. Thanks so much for listening.